Okay, hello Year 12s. This is just a fairly short video where I'm just going to be going through this section of interpreting slope fields. So in this section, this is probably one of the more common questions I've seen for Extension 1 in terms of this section on slope fields. What happens here is you've got given a diagram for a slope field that has been drawn. So in the last lesson, we actually drew slope fields and we worked around with drawing particular solutions on a slope field. In this section, what happens is they've drawn out a slope field for you, and you actually want to figure out what the differential equation is based on of the slope field. Now, for this, there's a few kind of like ways that I like to think. I like to kind of picture this, and I kind of like things that I notice when I'm trying to figure this out. So a few things for you guys to note, maybe if you would like to, like, this is kind of like what I like to note for. So I'm trying to notice where a few particular things, dy on dx, so our derivative, our differential is equal to 0. So that means we're looking for horizontal gradients on slope fields. And so what this means is that either you've got a function that means either x is equal to 0 or y is equal to 0 at those particular points. And so if x is equal to 0 or y is equal to 0 at that particular point, that just means whatever value is equal to 0 at that point, that means you got horizontal gradient, which is one of the things I notice. The second thing is I go dy on dx is undefined. And so here we're looking for parts where you've got vertical gradients. And so if that is the case, that means that you either got 1 over x is equal to you've got x is equal to 0, where you've got actually a better way to write this is in your differential equation. And probably it's better to fix up these ones as well. Dy on dx is equal to x of some sort, or dy on dx is equal to y at those particular points. And the other thing is here, this is equal to 1 over x, and so that particular points, you've got 1, when you have 1 over x is equal to 0, where x is equal to 0, and maybe we should write where x is equal to 0, y is equal to 0, or 1 over y. Now the third thing that I try to notice is just if I can't work around with those, I just sub in coordinates into differential. So here, remember that both your x values and your y value will change the differential equation. And so we can actually sub in coordinates into our differential equation to help me figure out and look at if it's positive or negative, and then see how that may help me answer this. Okay, so let's have a look at this particular one. This is from the 2020 Extension 1 HSC sample paper, and it's a multiple choice question. The slope field for the first order differential equation is shown. And so here we've got the slope field. Which of the following could the differential equation be the differential equation represented? So here we get a few options, and here we've got a few things. So if you have a look at the first two, you've got x being divided by 3y, but the other two you've got x being times with 3y. So let's actually apply these steps and have a look at what's happening on my slope field. Now, if you have a look, there's a few things that I immediately start to notice on the slope field. Notice here, when we get closer and closer to the x-axis, so when we get closer and closer to the x-axis, we get closer and closer to a horizontal gradient. So here, the x-axis is where y is equal to 0, and here dy on dx is equal to 0. So our differential when y is equal to 0 is equal to 0. The second thing I also notice is that if I go towards the y-axis, notice here, it's getting closer. If you look at the dashes here, they get closer and closer to being horizontal as well. So the trend is they start to get more horizontal as we get towards x equals 0. So x is equal to 0, dy on dx is equal to 0. So what I can do here is I can just sub in y is equal to 0 and x is equal to 0. And if it gives me 0 in my differential equation, then that works out. Now immediately, that means I can actually eliminate one of these. So if you notice here, for the first two, if I sub in y is equal to 0 into either one of these, what will happen is you get x over 0, and that is just undefined. And so here for both of these, when y is equal to 0, so along the x-axis, what we would expect is instead of being horizontal lines, we should be expecting vertical lines, because undefined just means you have a vertical gradient, which is not the case here. And so that means I can immediately eliminate the first two solutions. So here I can eliminate this guy and I can eliminate this guy. And so I'm left with these two answers. So here I've got xy over 3, and it's either the positive version or the negative version. Now, once I've got that information, so I eliminated the first two here. Oh, let me see if my page overloads. Oh, where am I? Oh, we're a bit far up. Once I've eliminated those first two solutions, the way I did that was by noticing that along the x-axis, the gradient was equal to 0. So here, as we get towards the x-axis, all the gradient dashes, if you just keep following the trends that you see on the slope field, it would become horizontal. And that meant that y is equal to 0, dy on dx is equal to 0. And on the y-axis, we noticed we had horizontal, and that means that x is equal to 0, dy on dx is equal to 0. And so we could eliminate the first two answers there that way. Now, the last two answers, we want to figure out if it's positive or if it's negative. Now, a way that we can do this is by picking a point on my Cartesian plane. So let's say over here, 2, 2. If I go to 2, 2 over here, what do we notice about the gradient? Oh, the gradients at 2, 2 are negative. So what I need to expect when I sub in 2, 2 is that my derivative, so at 2, 2, dy on dx is negative. So that's what I need to kind of maybe I'll put this up on here. I'll put it here. At 2, 2, dy on dx is negative. It's going to be negative. So we want to actually find a value. When we sub in 2, 2, we're going to get a negative value. So if you have a look here, that means I can eliminate another one of these. So I can actually eliminate C, because if I sub in 2, 2 into dy and dx is equal to xy over 3, that gives me 2 times 2 over 3, which is 4 over 3. And that's actually a positive value. And so here, if we actually graph this one, we would expect that we could see a positive gradient. And that's not what we see here. It's actually a negative gradient at 2, 2. And so here, that leaves me with a final answer of D. So often with these, I kind of use this process of elimination by kind of noticing a few of these kind of three main things. So we want to see whether derivative on our slope field is horizontal. And so that means that x value or y value at that particular point is equal to 0. And so, and then the next thing is then I go, okay, well, I'm looking for when the gradient is undefined. And so I'm trying to look for where, where you've got vertical asymptotes. So vertical gradients, and that just means 1 over x, or that means it's at the bottom of my fraction. So here the denominator is equal to 0. Okay, cool. So we've got D for that one. Let's have a look at the next one. Next one is from the 2014 VCE specialist paper. The differential equation that is best represented by the above direction field. So this is below in this case, and is. So here we've got a whole bunch of differential equations, and once again we've got a slope field, and we want to try and notice a few things here. Now, if you have a look at the graph here, there's not many points that I can see immediately that are horizontal. So there's not many you can keep going downwards over here, and you'll start to see it eventually get horizontal, but we don't have any particular patterns there. So immediately, that's the first thing that I was saying, looking for horizontal gradients is a little bit out. Next thing is I want to try and look for vertical gradients. Now, if you have a look here, there's actually, it's a bit hard to see, but there's actually this vertical gradient trend. So if you have a look here, we've got a bunch of vertical gradients, but this time they don't actually form at an x value or a y value. They form along this line. Now, if you think about it, what is this equation of this line going to be? Well, it passes through the origin, and it keeps going up like this, like so. Now, we don't have any x or y values, but if you have a look at the graphs on here, well, what we can kind of predict is, well, this is something. This graph is these gradients, these positive gradients, vertical gradients, they form along a straight line that goes through the origin. So this is the line y is equal to x, or mx in that particular case. And so what that means is that here along dy and dx, we've got dy on dx is equal to 1 over, well, this guy needs to be equal to, so I'm just going to rearrange this. So this is y minus x is equal to 0. And so we need to let, it means it needs to follow this particular pattern. Or, in the other, if it's negative, the other way, x minus y. The reason being is because here, this equation for the line, they've created this vertical asymptote. So if we know, let me actually try that again. So here we've got y minus x. Oh, this line y is equal to x, and so that means that if I rearrange it, we've got y minus x is equal to 0. And so if I put that in, if y minus x is equal to 0, then that means that, and we've got this vertical asymptote at this time, vertical gradient along this line. That means that if I do 1 divided by y minus x, which I know is going to be equal to 0, that will get me vertical gradient, because if I want a vertical gradient, I need dy and dx is equal to 1 over 0 of some sort. So here, that's why I'm going to get this particular equation. So that means I can actually eliminate this one here, and this one here. Now the reason why I've also included this second one is because I can also rearrange this and I get x minus y is equal to 0. So I can actually include the second version as well. So that leaves me with these two equations. Now, if you're trying to tell between the two, all we need to do is just sub in a point and just see if our gradient at that particular point is positive or negative. So let's take, like, for example, a positive. So they don't give us any numerical values here, but we just want to pick a random number. So let's say I pick a positive number and a positive value for x and a positive value for y. So if I have a positive value for x and positive value of y where in this case, x is bigger than y. If I want to take something over here, x needs to be bigger than y. So here, if I sub in, let's say, like 5, 4 or something. 5, 4. Oh, 5, 5, 1. Let's put 5, 1. Notice here, the gradient is actually negative. So what I want is a negative gradient. So if I sub in 5, 1 into this first one, I'm going to get 1 minus 5 at the bottom, which is negative 4. So this is going to be a negative value for this first one. But if I sub it in the second one, I get 1 over 5 minus 1, which is going to be 1 over 5 minus 1. So this one was 1 over 1 minus 5, which is 1 over negative 4. So that's negative. And this one is equal to 1 over 4, which is positive. And so if you have a look at the slope field at that point, it's negative. So that means I can get rid of this guy as well. And so here I'm left with this. Oh, hang on, not that one. I can get rid of this one. And so here I'm left with this one here. Okay. So here for this slope field, I actually noticed that I had a few vertical gradients. So if I have a vertical gradient, I just want to find the x values or the y values at that particular point. So if, for example, yeah, sorry, I probably should have explained this better when I did it here. When you see vertical gradients, you just want to find an equation for when that is equal to 0. So for example, if instead I had a whole bunch of vertical gradients, x is equal to 4, that means I go, okay, x is equal to 4, I rearrange it, x minus 4 is equal to 0. And so that means your derivative is going to be equal to 1 over x minus 4 at that particular point, because you've got the whole bunch of these vertical gradients. For this particular scenario, because this is happening along a linear relationship, so here in this case it goes through the origin, so y is equal to x, for example. So here I'm just rearrange that like so, and then in this case it was y minus x, 1 over 1 minus x, y minus x. Okay, cool. So we used the vertical gradient fact, and then we just had to sub in a random point. Here you had to make sure that you actually picked a point that was in and looking at the correct spot. In this particular area here under that line, we had x is bigger than 0, 4. X is bigger than y, and so here I subbed in like 5, 1. But if I picked a value above this line, I would have to pick something where it's y is bigger than x, because here, any point above this point, so here for example, if I'm here like that 2, 1, that point would make sense here. But 2, 2 is actually on the line here. So if I go anything further, it'd be under the line. And so if you notice the shape at those particular points, it looks a little bit different. Okay, so that's this next example here. Okay, cool. So hopefully from these first two examples, you kind of see this is like kind of like a process of elimination, and you just try and use a bit of logic and based on the shape of the graph to figure out what type of differential equation is being represented at all. Okay. Let's have a look at this next one. The direction field for a certain differential equation is shown. So here we've given the slope field for that particular differential equation. The solution curve to the differential equation that passes through the point 2.5, 1.5 could also pass through. So what we're doing here is they're telling us that we want to find the particular solution that goes through 2.5, 1.5. So here I'm going to put in 2.5, 1.5. So 2.5 is over here, 1.5 is over here. And so what we want to do is figure out what other points could go through the same solution curve that would go through this 2.5, 1.5. Now, if you just drew the based on the gradient, based off of the slope curve, if I just follow the shape of it, so here I'm just in between these two, kind of going down here, and then kind of goes up like that on this side, and then down on this side, it kind of just goes down like so. And so here, this is kind of what the solution curve will look like. Okay. So let's see which one of these points in the answers will actually go through. So let's start off. First one, A, 0, 2. So 0, 2 is over here. Now notice 0, 2 is not going to go through my solution curve. So I'm just going to ignore that. Okay. Next one is 1, 2. Now 1, 2 is up here. Now it's fairly close to my solution curve, so it might be the one. But I'm going to be a bit tentative on this. I'm just going to put that there as a question mark. Okay, next one is 3, 1. Now, next one, 3, 1. Actually, I should have done this in different colors. So this one's a question mark. 3, 1 is over here. Now, 3, 1 actually goes through the exact solution that I drew. So I'm like, oh, this one's a fairly maybe. Like maybe it's going to be that. I just want to make sure that the other ones aren't likely going to be on my curve before I commit to this one. Okay. Next one is 3, negative 0.5. So 3, negative 0.5, hopefully you can already notice, is going to be immediately out. It's all the way down here. Our solution curve doesn't go through that one, so this one's out. And the last one is negative 0.5 and 2. So negative 0.5 is over here, 2 is up here. That's also a bit far from my curve, so I'm just going to eliminate that. And so we're left with these two. And here, just based on the fact that like my blue dot actually got on my line, which my solution curve that I drew, I'm just going to be like, okay, it's going to be C. And so here I'm just going to eliminate. So for this particular one, we just need to follow the differential. We have to follow the slope field or the direction field. So like we did last lesson when we were drawing solutions for a differential equation on a slope field, we just drew it on there and like followed where the lines went and kind of gave me the shape of my differential, my solution curve for that differential equation. And so here for this one, it just happens that 3, 1 is probably the best answer for our curve here. Okay, cool. Okay, excellent. Let's have a look at the next example. Example 23. The differential equation that represents the direction field below is. Okay, so this is another example of try to figure out what the differential equation is for our particular curve. Now here, there's a few things that I immediately noticed. So let's have a look at a few things. Now, first thing I noticed when I did this one was, once again, we've actually got another vertical gradient section. So if you have a look here, I've got vertical gradients along here. So if you have a look, I've got a few vertical gradients like here. Wait, that's not right. It's kind of like this one here is vertical. That's really not vertical. I can't it's like you've got a bunch and it kind of forms like this vertical line, like a linear relationship again. Yeah, and I've got down here kind of this one. Now, because this time we've got numbers, we can actually figure out what this particular linear relationship is. So I can draw a line through those and figure out, based off a few points here, what this linear relationship is. So if you have a look, we've got like 4, 8 is on this line. We've got 2, 4 roughly here is on the line. 1, 2 is on the line. And so here, this is going to be a straight line with the equation y is equal to 2x. Y is equal to 2x. Now, just like we did before, I'm just going to rearrange it. Y minus 2x is equal to 0. And so what this actually means is actually I've got a differential equation where that involves some sort of number 1 over y minus 2x, or I can also have the flipped version, 1 minus 2x minus y. Because we've got a whole bunch of vertical linear relationships that are equal to vertical gradients, that means it's on the bottom of my denominator. So here I've got this bottom part of my denominator makes up that. And so what that looks like is, if I look at my solutions, I can immediately eliminate this one over here. Everything else has that thing at the bottom. So we've got y minus 2x, 2x minus y, 2y minus x. Oh, hang on. Which one can I eliminate? Oh, I can also eliminate this one as well. I forgot that I could eliminate this one. So I can eliminate C and E, because these ones don't match up. So I've got these guys which all have the similar kind of different similar denominator, which is exactly what I want. Okay, cool. That's the first thing I noticed. The second thing I noticed, where was it that was what I wanted? Okay. What's the next thing I noticed? Is there any horizontal ones? I thought there wasn't, but I could be wrong. Okay, so when I did this, I didn't notice any oh, there is kind of one. Okay, so here, the other thing that I start to notice then is actually we've got a few that are kind of a horizontal trend as well, horizontal what's it called, gradients at a few points here. So I've got horizontal one here, kind of horizontal there, horizontal here, and you start to notice that these ones start to get a little bit more horizontal, but you're kind of looking for the real flat one in that scenario. So here we've got one super horizontal. I think it's either here or here. You've got another one that's super horizontal. Okay. And I think there's a final one over here. And there's one around here somewhere, but whichever one is super horizontal. Now we're trying to figure out the line that goes through it. It's kind of like this. So we've got this line here is y is equal to negative 2x. And so what this means is, well, if I've got that, that means that y is equal to negative 2x, 2x plus y is equal to 0. And because in this particular scenario, so dy on dx, we want it to be equal to 0, that means it's equal to 2x plus y. And so when we combine it with the previous fact, that means that we are actually looking for a differential equation where we've got 2x plus y is equal to, at the top, because I want this guy to be equal to 0 along this line, divided by either y minus 2x or 2x minus y. So here at the top, I want a variant of 2x plus y, or the other version that you could also get is y plus 2x. So at the top, I want y plus 2x or 2x plus y. So here I can eliminate this guy and this guy. And so here I'm left with just a. So here, if you ever see a point where your gradient is equal to 0, so dy on dx is equal to 0, that means that we want that particular line is equal to 0 as well. So here we had y is equal to 2x, when y is equal to negative 2x. So here y plus 2x is equal to 0. And so here I just want that in the top of my fraction for this scenario. So yeah, that was what we noticed here. If you wanted to, you could also just sub in points, and you would hopefully, you can also just deduce from there this particular scenario. Okay, cool. So that's it for this example. Let's have a look at one more. Oh, actually, there's two more. Actually, I'll have a look at this last one, and then I will get you guys to have a go at the next one on your own and see how you guys go. The differential equation that has a diagram below as its differential field is. Okay, so here we've got, it's looking hella trippy. It kind of looks like one of those eye trick designs, but here let's have a look at what we've got here. Now what you notice is, if you have a look at all of our graphs, look at all our possible solutions, they're dealing with trig functions here. So I'm gonna it's immediately telling me, okay, cool, I've got a whole bunch of trig functions that I'm going to be having to deal with for these questions, and so that's why it's got this repeated pattern, because if you remember with trig functions, it kind of is it keeps repeating over and over and over again. Now immediately, just by looking at this graph, I can immediately eliminate two of them. There's two of them that I can eliminate for an obvious reason. I'm going to eliminate D and E. The reason why this is the case is because they've got the functions in the bottom in the denominator. Now, if you remember your cos graph or your sine graph, no matter what the y value is or the x value is, doesn't matter what this is, but eventually you're going to get a value of what's it called? Your sine graph is eventually going to go to 0 at any particular point, or your cos graph is going to go to 0 at some point as well. They don't match up there, but this is just for the sake of drawing. And if you divide by 0, that means that your graph is undefined, and so you should expect to see on your graph a whole bunch of these vertical gradients. Unfortunately, if you have a look on the graph that's actually on the slope field that's actually given to us, there's no vertical gradients. And so here, that means that, to me at least, that's the first thing I notice. I'm just going to eliminate those two because I have got no vertical gradients to work with. Okay, so that's how I can eliminate two answers already from my from my multiple choice. Okay, so from here we need to figure out which one of these three is it. Now notice in both of them I've got this y is equal y minus x or x minus y, and so what this means is if I look at the line of y is equal to x, well that just, if I look at y is equal to x, which is this line over here, that means that y minus x is equal to 0. So if I sub in 0 into any of these trig functions, that can tell me the gradient at those particular points along the line. Now if I sub in 0 into sine, what do I get? Well, sine of 0 is equal to 0. And so what I should expect to see on this line for these sine ones is horizontal gradients. So I should expect to see a whole bunch of horizontal gradients along this y is equal to x line. But what do you notice? Actually, it's a whole bunch of lines which don't actually have a horizontal gradient. If you look along this y is equal to x line, it's actually going a positive vertical, gradient. So that tells me I can actually eliminate A and C. And so let's just check that our the last one is actually correct. If I get cos of 0, that's equal to 1. Now if you ever look at the gradients that along that y is equal to x line, they all have like a gradient 1. They kind of looks like a gradient 1. And so here, this just tells me that, oh, actually, this is a solution I'm looking for. It's B. It's going to be B. Okay, so that is that for that particular question. Let's have a look at the final one. So here, when you're trying to identify the graph of the differential equation from the slope curve, you're trying to look for a few patterns that you'll notice in your graph. Either in the multiple choice solutions that you get. This one actually worked from the multiple choice solutions and went back to the graph, as opposed to the previous one where we're like kind of working from the graph and moving towards the solutions. And so here I kind of noticed there's these patterns along this y is equal to x line, where it's just like it doesn't work out well for a few of our particular solutions, and also there's no vertical gradients. Okay. Let's have a look at this last example. Sketch possible solution curves to the slope field to the differential equation below. So here they've given us a slope field, and what the first part here, we just want to draw solutions to the slope field. So you can go from anywhere. You can just pick a point and just start and then just follow the slope field. So for example, if I started up here, I would know, oh, actually it starts to go up and up and up and up. So that's an example of one solution. You could start from over here and you could be like, oh, I'm going down. And then suddenly it balances out to here, like that. Okay, or you could go like somewhere over here, and let's say, oh, hello. It's starting to go across, and then as we get there, it's kind of going towards that value there. Okay, cool. So that's an example. All you need to do is just follow the slope field, and based off of the graph that you've got. Okay, next part B. From the slope field, identify any constant solutions, that is equilibrium solutions. So what we're trying to do is notice if there's any points where it's just like, if you had a solution there, it would just keep going, like it wouldn't move. And what you notice, hopefully, is if I erase this, is that there's actually these like 2 points along the slope field where you can just like, if you follow the slope field, so let's say if I picked a point here, if you follow the slope field, actually, you'd actually probably go like along here, you're going flat. And same with over here. If I pick the point there along my slope field, it's going flat. And so here, what are those constant solutions? These constant solutions are just along y is equal to -2 and y is equal to 2 up at the top there. And so that kind of makes sense, because if you sub those two values into your differential equation, you're just going to get 0. So if I subbed in 2 into here, y is equal to 2 into that, y is equal to y minus 2, you're going to get 0. And if I subbed in negative 2 into y plus 2, you're going to get 0 as well. So here, those two are my constant solutions. Okay, substitute into D. Oh, I literally just did that. So here, if we substitute those two values in, you would get 0. And hopefully you're good at doing that. I'm just going to go over the next part to kind of like save time. Okay. If the horizontal axis is time, describe the behavior of the solutions near those constant solutions and distinguish between them. So if they're saying if we think of the horizontal axis as time, and because time starts from 0 onwards, we're going to ignore the negative part. We're just going, okay, what happens if we have, what happens to the behavior, what happens to the solution curves near those constant solutions, and what happens, distinguish between them. So what you actually notice here is actually you've got three groups of solutions. So the first one is if your y value is greater than 2. So if your y value is greater than 2, you start close to 2, or start from wherever, and you just move away from 2. So here, the first one, if y is greater than 2, then this curve moves away from y is equal to 2 as time goes to infinity. So what you notice is if you have a y value which is above 2, it just moves away. If you have a solution, however, let's pick a solution between negative 2 and 2. Like if you have a look at any solution between negative 2 and 2, what you'll notice is that it'll start and it'll move towards negative 2. So like if I picked any point, so if I started at like 0, for example, what you'll notice is that we move towards negative 2. So everything between negative 2 and 2, like even if I go towards here, it moves towards that solution. So here, if y is between negative 2 and 2, then curve will go towards y is equal to negative 2 as time goes to infinity. So here, y goes to negative 2 as t goes to infinity. And the last case was if you have a solution that's below negative 2. Now here, if you've got any solution below negative 2, actually it will move upwards and go towards negative 2 as well. So if you have a look here, all these solutions, no matter where we start below negative 2, it's actually going to move towards y is equal to negative 2. So here, if y is less than negative 2, then as y will go to, as t goes to infinity, we should have done t goes to infinity. Oh, actually, it doesn't make a difference. Y will also go to negative 2 as t goes to infinity. So that's how we can answer this particular scenario. So here we actually just had to look at a few different cases and see what happens as time goes onwards, or we go towards the right. Okay, hopefully that helps. I'll post up a couple questions for you to have a look at for this section. And if there's any questions that you're not sure about, feel free to ask me. I'm more than happy to help. But yes, that's it for today's lesson, to make up for the last two lessons. And in the next lesson, we're going to be moving on to the next section. So I hope to see you guys then. Bye.